Okay, so today we're going to start to talk about probability and find probabilities. Um, we've we've had some background. We've looked at sets. We've looked at um, what intersections, unions, and complements are. We've taken a little detour and looked at how to count things because we're going to need to know how to count things when we get to probability. And so now you guys are ready to take a look at probability. Um, So random experiment is one which has an outcome that's uncertain. And in life, there's lots of things that can be uncertain in the short run. Okay, um, and that's could be an exciting thing. You know, with games or gambling or lotteries or those kinds of things that you have no idea what the outcome could be, and it's exciting for some people that hey, it could happen, right? Um, but the nice thing is with probability is it's kind of the mathematics of uncertain things in the long run, right? So if I flip a coin, what's the probability that I get tails? 50%. You guys are coming up with that already. But what does that mean? Does that mean if I flip a coin 10 times, does that mean I'm going to get 5 tails? No. So what's the big deal then? I mean, what's the use of that number, 50%, if I'm not getting 50% when I flip a coin 10 times? The equal chance is kind of the theoretical idea where it's coming from. But what happens is probability doesn't really work in the short term. It works in the long term. So although in 10, if I flip a coin 10 times, there's lots of outcomes that I can have. But if I flip a coin 10 billion times and I ask you what proportion of tails, guess what? I guarantee you it's going to be super close to 0.5. So the more times you do it, the closer it can't get away from that 0.5 as easily. Right? It gets kind of stuck at that 0.5. It doesn't have to be exactly 0.5, but it's going to be really close to it the more times you do it. And that's why casinos make money. Because in the short run, anything can happen. Anybody could win money, right? But they know the mathematics behind it, and they know in the long run, when a lot of people play, it's a sure thing that they're going to make money in the long run, as long as nobody's cheating the system. Okay, and so actually, kind of the origins of probability came out of casinos asking a guy named Blaise Pascal to come up with some mathematics behind the games. Um, but it's not just with games. It's with anything in life that's uncertain, where we want to put some numbers to it. Okay, the court systems use probability, schools use probability, um, more in statistics, but probability is the mathematics behind statistics, and so it's a decision maker mathematics, and we're just going to scratch the surface. We're just going to look at some really basic things. We're going to talk about coins and dice today, and work our way up from that. Okay. Um, so first, let's take a look at coins. Um, if you throw a single coin, you can get heads or tails. We write that we list their outcomes and put it in a set notation. If you flip 2 coins, again, you got 4 possible outcomes. The first coin could be tails, second coin could be tails. You could have tails heads, heads tails, and heads heads. Tails heads is going to be different than heads tails because you got 2 separate coins, and you do 2 different ways to do that. And so there's 4 possibilities. If I had 3 coins and I wanted to list out my possibilities, how many possibilities would I have with 3 coins? This is a counting question, right? You guys have practiced counting. So 3 coins, how many different ways? So some of you are thinking 6 because, hey, 1 coin there's 2, 2 coins there's 4. But look, if you have 3 coins, you could have heads or tails times heads or tails times heads or tails. And you have 8 ways or 8 possible outcomes when there's 3 coins. 5 coins? 32. 2 times 2 times 2 times 2 times 2. 2 to the 5th power. There's 32 outcomes when you have 5 coins. Okay. So a sample space is you listing out all possible outcomes of whatever experiment you're looking at. And so flipping a coin is an experiment. We don't know what the outcome is going to be. We can look at that, but listing out all possible outcomes of that experiment would be a sample space. So if we throw a fair die with 6 faces, what are the possible outcomes? 1, 2. All right, so that's the sample space of rolling one fair die. Now, if I roll 2 dice and I want to list the outcomes, how many outcomes would I have with 2 dice? 36. So it grows pretty quick. If I have 3 dice and I want to list those, how many outcomes do I have? What's that? Do you know how to how to figure it out though? It would be 36 times 6, which is 216 different ways just with 3 dice. So it grows pretty quickly, right? And you're not going to want to list out all those ways. But let's throwing 3 fair coins. How many ways? 3 fair coins. 8 possibilities. List all 8 out. Okay, you know there's 8. List them out. So the first one, maybe you're going to say tails, tails, tails. That's your first one. And then you should have 7 more. No, they're different. Because you have 3 different coins or 3 different tosses. 8 ways. So if you got all 8, you know when to stop when you get 8, right? All right. So tails, tails, tails. What's another one? Tails, tails, heads. Second one. What's another one? Tails and 2 heads. Okay. Tails, heads, tails. Heads, heads, heads. Heads, heads, tails. I got tails, tails, tails. What am I missing? Heads, tails, heads? I have 7. I need one more. Heads, tails, tails. Okay. So I listed them out just with you calling out, but personally, I like to do it in an organized way, especially when it gets to be more than 8 ways, right? And probably one thing I would do is I'd say, okay, how many ways can I get 3 tails? I just list that out. And then I say, well, how many ways can I get 2 tails? List all those out. How many ways can I get 1 tail? How many ways can I get no tails? Just by separating them into categories, then I know I've hit everything I need to hit, and I'm not repeating something that's already up there, because I want to keep looking back at everything I've done. Right. So what's this called? What do we make? a sample space. We listed all the outcomes, so it's called the sample space. So when you have a sample space, and assuming they're equally likely, and that's what we're starting with, okay? We're going to assume equally likely, and later on we'll change that. Not today, though. So there's 8 possible equally likely outcomes. So if I say, hey, what's the probability that I get all 3 tails? What's the answer? 1 out of 8. That's the probability. If I say, what's the probability I get exactly 2 tails? How many have exactly 2 tails? 1, 2, 3 out of 8. So the probability would be 3 out of 8. So if you have your sample space in front of you, it's as simple as counting, like simple counting, right? If it's small enough, I got 3 out of 8. That's it. That's your probability. Okay. This next part I'm just going to summarize, but we kind of talked about this. This is saying probability is a long run thing. Like in the beginning, if you're flipping a coin just a few times, you can have more variation in your outcomes. But the longer or the more times you flip that coin, it's gonna stay closer and stay around that theoretical probability, which is 0.5. And that's what that's saying. Now, there is a difference between theoretical probability and experimental probability. And if I take a paper clip, okay, and I bend this paper clip in a certain way, there it is. All right. Now I want to know what's the probability of like this. I have no theory to help me with that, right? None at all. But I could figure out the probability. How? Drop it a bunch of times and record, and I have to do a bunch of times. So let's do a couple million times, right? And I out of a couple million times, I record what's the proportion that it lands that way, and it may not be the exact probability, but it's going to be pretty close. Okay, and in life, there are scenarios that businesses run into, and they want to know the probability of something, and there's no theory to help them. And so they hire a computer programmer to create a virtual situation like the real one. And they tell the computer to run it a few million times to see what happens. And they calculate probabilities that way. So that's experimental probability. Okay? So on number 2 here, we're going to pay attention to the wording here. It says find the experimental probability. It doesn't say find the theoretical probability. Okay? And so there's a distinction that needs to be made. When it says experimental, you're just relying on the data that you have in front of you. Drop all theory. Okay? So here we roll the standard number cube 10 times. Here are our 10 results. So if that's all you have in front of you, and you have to come up with an estimate for the probability of rolling a 5, you're going to just count how many 5s you got out of 10. And I got 1 5 out of 10. So my guess or my estimate would be 1 out of 10. Is it right? Well, it's my experimental probability. It's an estimate. But in theory, what should it be? 1 out of 6. Okay. So the theoretical probability would be 1 out of 6, but in this experiment, I got 1 out of 10. Probability rolling it even, what would be the experimental probability here? So you count your evens, you count a 7. We got 7 out of 10. But theoretically, what should it be? Three out of 6, which is 1 out of 2, 50%. Okay, so in the long run, that's what this experimental probability will turn into. So if I did this millions of times, it would get closer and closer to that number, assuming it's a fair die. So an event is something you're interested in. It's so if you're in this case here, we're throwing a die. We can have 6 possible outcomes. It could be a 1, 2, 3, 4, 5, or 6. So an event would be a subset of that. So it could be just rolling a 1, or it could be getting a score of 3 or more, which would be 3, 4, 5, or 6, which is a subset of our sample space. Or it could be what's getting an even, right? And so the events are subsets of your complete set, which we used to call it. What was the name of the complete set when we were studying sets? S was the variable, but it was called the universe, right? So the sample space is the universe at hand here, and so you take a subset of that. And remember what complement means? Everything else, right? So in words, we're going to state what the complements of these would be. We're not going to list them out. We're just going to state what they would be. And something that comes up a lot in math, and you want to know what they mean, not just in probability, but it'll come up in other cases too, is the word at least and the word at most. And not just in math, but we use that in everyday language as well. What's another way to say at least? Okay, let's think about that. If I said at least, you're thinking minimum. That's good, right? Because if I say I have at least $10 in my wallet, that's the minimum. I could have $10 or more, right? So minimum's a good way to put it. Or what else? Greater than or equal is another way to say at least. Okay. If I say at most, how would you do that one? Maximum or less than or equal to. Okay. So so here's an event. A is the event that we have 2 heads are obtained out of 3 coins. Okay, toss 3 coins. What's you're looking for the event, you get 2 heads. What would be the complement of that? Oh, careful. That's tempting. Is the opposite of 2 heads 2 tails? No. What would be the opposite of getting 2 heads? Okay. Just that? Or no heads? Or, well, no heads is 3 tails. Or 3 heads. Okay? That would be the complement. Everything else that's possible. Okay? What's the complement of at least 2 heads are obtained? What would be the complement of at least 2 heads obtained? Yeah. At most, they're not complements because they actually have an intersection. At least and at most share the equal. Okay, so remember what at least means? At least means more than or equal. So what's left? If it's not more than and it's not equal, then it's less than. So 1 or 0. So you can say 1 or 0, or you can say less than 2 heads. which would mean 1 or 0. Okay, so that's the complement. What would be the complement of at most 2 heads? More than, which would just mean 3. So okay. We're still going to use some of that notation. We'll use A prime to represent the complement, capital A to represent an event, but which represents a subset or set. So if we're working with equally likely outcomes, that's key right there. Got to be equally likely, because everything changes if it's not equally likely, okay? But today, everything's equally likely. If we're working with equally likely outcomes, then we can define the probability this way. It's the number of outcomes in your event divided by the total number of outcomes in your sample space. Okay, so this is number in the event over the number in the sample space. And could this number ever be bigger than 1? How? If so, you'd have to have more numbers, more outcomes in your event than in your sample space. Is that possible? No, because your event is a subset of your sample space. So you're never going to have a probability bigger than 1. And you're never going to have a probability less than 0. What happens if your probability is 0? That means there's nothing in your event. It's the empty set, right? Which means it's not going to happen. It's impossible. What happens if you get a probability of 1? Means everything in your sample space is in that event, and so it's going to happen. It's for sure. Okay. Most of the time, probability is not 0 and it's not 1. It's in between. Okay. So number 4 says, for each of the following events, A, B, and C, list and count the number of outcomes, and then calculate the probability of each one. So take a few minutes and do that. Okay, so what are you guys getting for A, for the probability? 2 out of 3. How about B? 3 out of 8. How about C? Okay, 0. Because if the maximum you can get if you roll 2 standard dice is 12. You can't get 14, right? And so on A, you can get a 3, 4, 5, or 6. So if you count that, that's 4 out of the total 6 in the sample space. Reduce your fraction to 2/3. B, you got three cases in your event, but remember there were 8 total. We listed the sample space prior, and so 3 out of 8. And there's no way that C can happen, so the probability is 0. Okay. So I'm going to leave 5 and 6 for homework here. Let's talk about 2 dice. because a lot of your homework is going to be on dice problems, and I want you to see a couple of these with me before you try them on your own. So let's start with number 9. If 2 standard dice are rolled, what's the probability that the resulting sum is greater than 3 and less than 11? Think about that. What would you do? What do we need to do that one? What's that? Okay, you can't get a 6 and a 6 because that would be 12. But there's lots of things we can get, right? So how do what are we going to have to do? So what would make a 3? A 1 and a 2 and a 2 and a 1. So you could, okay, there's 2 that can make a 3. What would have to make a 4? A 1 and a 3, a 2 and a 2, a 3 and a 1. So we could do that. It's going to be a lot, right? We can count them very carefully. And then once we count them all, what are we going to put it over? There's 36 different sums. Now, here's what I tend to do. When I have a 2 dice problem, I create like an addition table. So the first one I can get a 1, 2, 3, 4, 5, or 6. The second one could be a 1, 2, 3, 4, 5, or 6. Remember these addition tables from elementary school? And I fill out all the possible sums. It's compact, it organizes everything, and it's easy to count. After you do it a couple times, you can do it pretty quickly. So now I have all 36 possibilities right in front of me that quickly, and I can count what I need to count, right? And I want to count greater than 3, so 4, 5, all the way up to, but it's got to be less than 11, so all the way up to 10. So I want to count everything here. Now, if I have something where there's a lot of things I need to count and there's a little left over, I tend to take the backdoor approach and say, well, if there's 36 numbers here and 6 of them are not highlighted, then I know how many are highlighted, right? 30, right? Instead of having to count all 30 of them, I tend to take the easier approach. So this is for number 9. We've got 30 that are highlighted out of 36 total, and reduce that to 5 over 6. That's our probability. And so we label this is the probability of getting a sum between 3 and 11. So I'm going to do this. 3 is less than my sum, which is less than 11. Okay. So as you're working through the 2 dice problem, that may be a tool that you want to use. It depends on the problem. There may be an easier way too. Every problem's a little unique, okay? And once you make it once, you can use it for other problems. Let's skip now to 3 dice problems because you have some 3 dice problems on your homework too. Let's look at 16. A standard die is rolled 3 times. What's the probability that all the rolls show a number that is a power of 2? Okay. So first of all, how many possibilities are there, or how many in the sample space? So 6 times 6 times 6 is, what did we say, 216 possibilities in the sample space, right? We don't want to list them all out. And now we're interested in this event that we get a power of 2. What does it mean to get a power of 2 when you're rolling a die? Yeah. Well, what are your powers of 2? Powers of 2 are 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third, 8. I can't roll an 8 though, but I can roll a 1, a 2, and a 4. So that's what it's saying. It's kind of a hidden way of saying all of them are going to show a 1, a 2, or a 4. Okay? So then you got to start to say, well, how can that happen? Well, I could have a 1, 1, 1. I could have a 2, 2, 2. I could have a, sorry, not a 3, 3, 3. 4, 4, 4. Right? So here's where the counting comes in. Sometimes we have quick ways to count. Sometimes you just list them out. If you guys think of a quicker way, you can, but I'm just going to keep listing them out until you do. Well, actually, is there a nice way to do it? Count it. So I'm going to roll 3. How many possibilities do I have for my first one? 3. How many do I for my second? Because I can repeat, huh? How many ways are there? Oh, that's so much better than listing all of them out. But you can list them out, right? So the counting's coming into is handy here. So we got 27 possibilities in our event. So what's the probability of getting a power of 2? 27 over 216. Now we need to reduce that. Now 27 is 3 times 3 times 3. And 216 is 6 times 6 times 6. And so we can divide out and we end up with 1 over 8. Okay. So they take some thinking and some counting and some working through, but I want you to try these. Number 7 to 21 is your assignment. I'll stop there.